detecting X-rays from some of the most exotic objects in the universe. This powerful research vehicle, called Astro-E, took 7 years to build, 7 long years of waiting, that culminated in the year 2000, when Astro-E would join 2 other X-ray observatories in orbit, NASA's Chandra X-ray Observatory and Europe's X-ray Multi-Mirror mission. While physically located on opposite sides of the Earth, the Japanese and American teams worked closely in pursuit of their shared goal. Together, they developed X-ray spectrometers, X-ray telescopes, and lasting friendships. Their hard work and careful planning led to this day, Launch Day for Astro-E, a day that would bring to each of them the realities of high-risk ventures like spaceflight.
It was okay for a while, and what happened was the lining of the rocket nozzle burned through.
And that first stage started to corkscrew.
The Japanese people started saying something's wrong.
You really don't know what happened to Astro-E.
It was seen at the tracking station on Christmas Island in the Pacific Ocean, and there's another tracking station in Brazil which did not ever get a signal from it.
So we think it's somewhere in the South Pacific.
We were all down. Remember, I couldn't even drive home. I mean, I got a ride home.
We all went out for karaoke and sang and cried with each other.
It was like a death in the family here.
You know, it's just a bunch of hardware, and so what? But then I realized it meant that I wasn't going to get to see these people again, maybe for a very long time. Well, by the time I flew back from Japan, we were all feeling a little better because by then we had decided that we needed to write a proposal.
We got a mail saying, hey, there is a meeting tomorrow and, you know, enough morning, now we're back to work.
Well, these things usually take 2 or 3 months to write, but we figured we could do it in a week.
The entire proposal was put together in a week's time, and it has become a model of proposals.
For me, it was just, I think, the most intense experience in working with a group of people that I've ever had.
That intensity paid off. They met the deadline. Their proposal so impressed NASA management that the space agency awarded the team their new mission.
And then the Japanese proposed a reflight of Astro-E. We would call it Astro-E2.
The American and Japanese space agencies decided to combine the 2 missions, reuniting the Astro-E team and setting them on a course to build the coolest X-ray satellite, Astro-E2. Let's meet these members of the Astro-E2 team.
There's a few of us at work that we have a little band. We're called Naked Singularity. The first time I realized I would kind of like to do this was when I read a story in Scientific American many years ago, maybe in high school, about the Voyager space probes and all the problems they had from the moment of launch up through the end of the mission. There was just difficulty after difficulty, and the way the people in the control room solved these difficulties so that all the public saw was the beautiful pictures. And I thought, this is what I would like to be doing.
I didn't even, as a matter of fact, dream about a job with NASA because that seemed like too big a dream. Well, I do have a degree in industrial arts education, which is what they call tech ed these days. But I had not applied that so much in the early years of my career. I had done a number of technical jobs and had spent several years as a car mechanic. But at some point along there, I decided I didn't want to be a car mechanic anymore. And I was living in Southern California at a place called Big Bear Lake, and it turned out there was a solar observatory at that lake operated by Caltech. And I applied for and got a job there. I did operate the telescopes and worked as an observer. I also did machining and applied these technical skills throughout the plant. So that's how I got into science, and then transferring that knowledge and skill base to Goddard.
This is a Trikey. It's a three-wheeler. It's a geek toy, I think. It's actually a neat physics trick. I grew up in Paris, and my parents took me to le Palais de la Découverte, which is like a science museum. And I remember one time, you know, there was this experiment where you take one ball and it goes, and then one ball goes up. And, you know, the guy said, you know, who can predict what is going to happen? And, you know, to me, it seemed totally obvious that if you take two, the two will. So I said that, and the guy goes, "You're good." And so then I thought, oh, I see. I mean, this is something I can do. It had occurred to me that physics was actually linked to anything that moved.
While not directly on the Astro-E2 team, NASA astrophysicist Dr. Kim Weaver is eager to work with Astro-E2 data. She explains what got her interested in working at NASA.
When I was 5 years old, we landed on the moon, and I was hit by a car that day and put in the hospital. And I remember being so upset that I was not going to see the moon landing.
That's one small step for man.
That was a fundamental turning point for me. Ever since that day, I wanted to work for NASA. So I'm here now, today. Astro-E2 is going to be looking at a number of things. It's going to be looking at supernova remnants to understand the chemical elements created when a star explodes. It's going to be looking at accretion disks around black holes to study the gravitational effects of the black hole on the accretion disk. It's going to be looking at the corona of stars. Our sun has a really hot corona that gives off X-rays, so we're going to be looking at coronae of other stars to study how they behave if they're similar to the sun. And also, Astro-E2 will look at clusters, the hot X-ray gas in the centers of clusters, to understand the temperature of the cluster, the mass of the cluster, and that way you can sort of probe the universe by looking at clusters of galaxies. X-rays are light. It's electromagnetic radiation, just like optical light, but it's at a different wavelength. The X-rays have a shorter wavelength, and they carry much more energy, so each X-ray photon has much more energy than an individual optical photon. In X-ray astronomy, it's not like going to a dentist. The dentist takes an X-ray by shooting X-rays at you, and on the other side they have a piece of film that collects the X-rays, and that's how you see the X-ray shadow. In astronomy, we're not producing the X-rays ourselves. The objects out there, the stars, the supernovae, the galaxies, the black holes, are producing the X-rays. And then we send up a telescope that just detects the X-rays. Black holes have extreme gravity, and they create a lot of intensity and heat and energy around them. And so the regions around a black hole are going to be producing X-rays as opposed to optical light. And so if you're going to probe a black hole, you need to be able to see X-rays. The galaxy is filled with all sorts of stars and gas and dust. And that gas and dust blocks our view to the center of the galaxy. So if we look at it in optical light, we can't see the center of the galaxy because there's all the dust in the way. But in an active galactic nucleus that has a huge black hole in the center that gives off X-rays around it in an accretion disk, you can use those X-rays to probe into the center of the galaxy, so you can see through the gas and dust. If you could see a black hole, it would cast a shadow to your eye. So you would see the disk, and you would see a little black spot in the middle that would be the shadow of the black hole. But what you're really seeing in X-ray light is the disk itself. The black hole has a huge amount of gravity, and so it brings material toward it. And what happens is it accretes material. Material comes in and falls into the black hole. And that's why you can see the black hole, because as material comes into the black hole, It also emits light and gives off energy.